morning, Professor Small.
Good morning. Can everyone hear me?
Yes, I can at least.
All right.
Yep.
Good. So the way we're going to be doing this is, first of all, it should hopefully be recording because I'm going to, yeah, it looks like it's recording. I'm going to post the recording on YouTube after this. Now I'm going to connect my other device, and because that's my tablet, which I can use for writing notes. I'm going to do most of my presentation with my tablet because I can write freehand and do things as we go along. Let's go to meetings, 600 lecture. All right, now I'm going to stop the video from my other connection. And we still have a few minutes. So let me go over my notes here. All right, got the chat ready. Looks like most people did the assignment that was due today. I graded it. I think partway through class we'll go over that, but I'm going to start with a few other things. Then we'll go, I'm going to start with something from Friday. Then we'll go over some new material on complex numbers. And then we will we'll go over today's assignment, and then we'll do some more complex number material. But we'll wait a few more minutes for everyone to log in. While we're waiting, any questions on anything other than specifics of complex numbers? Let's gain some. Why am I getting feedback? I thought I had this device disconnected. Yeah, audio on this device is off, so it's not that. All right.
Oh, you have a different background this time.
Well, yeah, I don't have my Slavic language essay excerpt. This is the methane lakes of Titan.
Oh, really?
Yeah, this is a map of the methane lakes of Titan. So NASA's Cassini mission mapped the methane lakes of Titan. You can't make a map of them with a visible light camera. The atmosphere of Titan is too thick. For those who don't know, Titan is one of the moons of Saturn. It's actually has a thicker atmosphere than the Earth. The atmospheric pressure on Titan is about twice the atmospheric pressure on Earth. It's a nitrogen atmosphere. And although Titan is way too cold for water to form vapor and rain, it is cold enough for methane to condense into a liquid. And so at the poles of Titan, there are methane lakes. Away from the poles, it's too warm and methane evaporates. But at the poles, methane can condense into a liquid. Sometimes it can form ice crystals. So Titan gets snow and rain made out of methane. And the big question is, what? Someone said something? So the big question is, and Adrian, sorry, my wife is in the background and she has something on her phone going off. Adrian? Okay. All right, yes, the realities of teaching from home. So yeah, Titan has lakes, and the big question is, well, there's liquid. Could there be some exotic bacteria? And of course, it would have to be very, 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 very exotic, because life as we know it depends on liquid water. Chemists who have looked at it seem skeptical for the most part, but then again, it's not like anyone has investigated this chemistry to the same depth that they've investigated the chemistry of organic compounds in water at terrestrial temperatures. And now it is 10:01, so let's get started. Before we talk about complex numbers, I want to go over something from Friday. And so, oh great, it's not letting me do polls from this because I've got two things connected. So I'm going to disconnect this device. And now we will see if I can do polls.
Your presentation mode is active, so we can see the next slide.
Oh, yeah, okay, good call. So how do I turn off? Okay, great. Solved one technical problem, but Zoom still thinks that I'm logged in from another device. Let me try one more thing. Okay. Nope, still not letting me do it. Okay. So I was hoping to do polls. We're not going to be able to do polls. So I'm just going to go over something that came up on Friday. Given that the logarithm of 1 is 0 and that the logarithm of 2 is greater than 0, true or false? Logarithm of 2 equals logarithm of 1 plus 1 equals log of 1 plus log of 1. Now, I'm not going to poll you. I'm not going to ask you to all shout at once into your microphones. But there was a lot of debate about this on Friday. This is definitely a false statement because the log of 1 plus 1 is the logarithm of 2. Whereas the logarithm of 1 is 0. So if we add up the logarithm of 1 and the logarithm of 1, we get 0. The lesson here is that the logarithm is a nonlinear operation. Okay, you can't take the sum of the logs and equate that to the log of the sum. So then this was a thing that people spent a lot of time debating on Friday. And this is most definitely false because the log of the sum is not the sum of the logs. Any questions? All right, then I have to switch back to my other device. I did not realize I would not be able to do all this polling like this. Next time I'm going to just operate from one device, but bear with me as I operate from two devices today. And there, start.
Good.
Continue this meeting. Now you can hear the, okay, I just disconnected the audio, turned off the video. I'm going to disable screen sharing here, start the screen sharing here, go to, all right. We're going to talk about complex numbers, and we have to talk about complex numbers because they're used all the time in physics to represent oscillating quantities. And from what I saw in the homework, there is a range of familiarity with the algebra of complex numbers. So let's start at the beginning. I is the square root of -1. So I squared is -1. And then I cubed is I squared I. And this I squared is -1. So I cubed is minus I. And then I to the fourth is just going to be I squared times I squared, which is -1 times -1, which is 1. And if it went to I to the fifth, well, that's I to the fourth times I, which is just 1 times I, which is I. And I to the sixth would be I to the fourth times I squared, which would be -1. So what you should see is that there's this alternating pattern. This is the beginning of the idea that complex numbers are related to oscillations. Because as we keep raising I to more and more powers, I to the seventh is I to the fourth times I cubed. And we already established this should be -I, not -1. So that's going to be 1 times -I, or just -I. So I to the seventh is the same as I cubed. And I to the eighth is the same as I to the fourth, because I to the fourth is 1. And so forth. But if all we did was just raise I to different powers, we're not getting very far. And oh, I should also add that although I encourage you to take notes, writing as you pay attention is the best way to retain things. I will also upload a copy of this. So don't worry too much if you don't manage to get everything. So complex numbers are usually denoted Z. And of course, this will cause absolutely no confusion with the third dimension in geometry, X, Y, and Z. We usually write complex numbers as A plus BI. And if we can do arithmetic with complex numbers, similar but not quite the same as we would do arithmetic with real numbers. If we had two complex numbers, Z1 and Z2, then Z1 plus Z2 would be A1 plus IB1 plus A2 plus, IB2. Or if we want to write this in terms of its real and imaginary parts, the imaginary parts are here and here, the real parts are here and here. So we have A1 plus A2 I times B1 plus B2. One thing I noticed was some confusion over what the real and imaginary parts of a complex number might be. For instance, what if we had z equals 7i? Well, some people on the homework started thinking that whatever real number they see in there must be the real part. Let's write this as 0 plus 7i, all right? This is the real part. This is the imaginary part. This came up because let's talk about 1 over I. Well, in order to figure out what 1 over I is, let's multiply top and bottom by I. Bottom is I times I. So I over I squared, or I over -1, or minus I. And some people just looked and said, well, you know, here's a real number, -1. -1 is a real number, that's certainly true. But just because -1 is a real number does not mean it is the imaginary part of this complex number. This is 0 plus -1 times I. So -1 is the imaginary part, and 0 is the real part. Any questions on that?
I got a quick question, Dr. Small.
Yeah.
Since I is in the denominator, weren't you supposed to multiply by the conjugate, so -I over -I?
Technically, yes. Well, supposed to. What does supposed to mean? Multiplying by the conjugate is the most efficient way to turn the denominator into a real number. It's the way that's guaranteed to work. In this case, because it was just I, it still worked. But yes, technically, I should be doing that. And we'll get to complex conjugates in a moment.
I have another for clarification.
Yeah.
So when you are asked for the imaginary component of a number, it's the coefficient next to I, not the coefficient next to I and I.
No, just the coefficient next to I.
Okay.
Yeah, so the imaginary part of, say, 5 plus 12i is 12, not 12i. And to some extent, that's a matter of definition. You could say, well, isn't 12i the reason why it's imaginary? Sure, a lot of this is notation. But when we get to absolute values, let's get to absolute values, and you'll see why. If we get to absolute values, that matters. So in order to talk about absolute value, we have to talk about geometrical representations of complex numbers. And we're going to do this on 2 levels. First with just real and imaginary parts, and then lengths and angles and complex exponentials. So this is the real axis, and this is the imaginary axis. And if I've got, say, this complex number, z, well, we could ask, how far away from the origin is this point here? And of course, we'd have to look and see how far along the real axis, the real part of z, and how far along the imaginary axis, the imaginary part of z, and then the length of z. This is called length. It's called absolute value. It's called the magnitude. It's called the modulus. It has many names. They all mean the same thing. The length of z is just the distance from the origin, the distance from 0. So that's going to be the square root of the real part squared plus the imaginary part of z squared, right? And this had better be a real number. Lengths are real numbers. Some people on the homework would say that the imaginary part, that the length of, say, 5 plus 12i. Well, they said that that's the square root of 5 squared plus 12i squared. And I want to emphasize that everything I'm doing here is wrong. When I write down a wrong answer to critique it, inevitably there's someone who comes to me after class and says, Professor, you wrote this thing down, and then I put that on the next homework and you marked it wrong, but you put it on the board. I'm discussing this as a wrong example to make a point. Much like chemists will sometimes talk about phlogiston as a theory of fire, or in relativity, everybody talks about ether. Or in economics, people talk about Laffer curves that only slope in one direction rather than two. So if you were to do this, you would get the square root of 25 minus 144, which would be the square root of negative 119, which would be 10 point something I. And this is wrong, right? If the way we wrote it was this, you would get a length that is an imaginary number, and that would be wrong. And even worse, let's suppose that z was 3 plus 3i. And we were to do it this way. And again, everything I'm writing down now is wrong. We would get that the length of z is the square root of 9 plus negative 9, or the square root of 0, which is 0, even though 3 plus 3i is most definitely non-zero. Any questions? So the right way to do the length is this. Or the square root of a squared plus b squared if we write it as z equals a plus bi. And of course, people always ask this, if we called the real part something else, maybe because we're doing a more complicated formula, then it would be the square of that something else other than a. And likewise, if we called this imaginary part something other than b, it would be the square of that. Now, let's talk about multiplying complex numbers. If we multiply complex numbers, then what we've got is z1 is a1 plus b1i, and z2 is a2 plus b2i. And so z1, z2 is a1 plus b1i times a2 plus b2i. And then we multiply this just like you would multiply binomials in algebra. FOIL, first, outer, inner, last. Do they still teach that term for this multiplication, FOIL?
Yes.
Nodding your heads, but when I was helping my nephew with his algebra homework last week, he was saying he didn't know FOIL. So I don't know.
Common Core is weird.
Now then again, my nephew has had some
These
behavioral
days.
problems lately, but you know, maybe he's just not paying attention. Okay, so we're going to get a1, a2 plus a1, b2i. Then we multiply b1i times a2. Then we multiply b1i times b2i. And the I squared, that's -1. So this is negative b1, b2. And so we are left with a1, a2 minus b1, b2 plus A1, B2 plus A2, B1, whole thing times I. Now, you can memorize that if you want, or you could just remember the procedure every time you're given two complex numbers. I have to be honest, I don't memorize A1, A2 minus B1, B2. I just do the procedure. Here's the key thing. The key thing is that the real part of Z1, Z2 is not equal to the real part of Z1 times the real part of, sorry, there's this button on my stylus that I keep accidentally pressing. The real part of the product is not the product of the real parts, and likewise, the imaginary part of the product is not the product of the imaginary parts. If you remember nothing else, remember that. Remember that you have to actually do all of the multiplication. You have to do all 4 steps of the multiplication. The biggest source of mistakes is people skipping steps, and it never works out well. Any questions? Okay. Then let's talk about complex conjugates. Complex conjugate just comes down to multiplying the imaginary part by -1. Basically, because if this is A plus BI, then this is Z star equals A minus BI. It just got flipped about the real axis. And it's a fair question to ask, why do we define this but not define some other conjugate like over here? Why don't we have a special term for that? Practical, doesn't come up as much. There's no particular reason why we couldn't define it. We could certainly write it down. I could spend some time thinking about Greek and Latin root words and come up with an appropriate name for it, but it just doesn't matter. It doesn't come up as much. It is useful for a few reasons. For starters, let's compute Z star Z or ZZ star. People tend to write Z star Z by convention, even though ZZ star also works. Multiplication of complex numbers is commutative. Z1, Z2 equals Z2, Z1. People tend to write it this way, Z star Z instead of ZZ star, simply because there are branches of physics. We're going to get to things with matrices where multiplication isn't commutative. And so in matrix multiplication, if A is a matrix and A dagger is what we call the Hermitian conjugate, don't worry, you're not going to see this on the next homework. It's going to be a few weeks. When we're dealing with matrices, A star A is not in general equal to A star. And in the branch of physics where we make the heaviest use of matrices, quantum mechanics, A dagger A, dagger is the word for this symbol up here, A dagger A shows up more than A dagger. So if you see people writing Z star Z more than ZZ star, it's not because it matters for complex numbers, but because they just picked up a habit from more advanced branches of physics. A bit like in language, there may be 2 grammatically equivalent ways of writing something or saying something, but one of them becomes more common in some dialect. I make a lot of linguistic analogies. It's sort of a hobby of mine. But, you know, for instance, in Spanish, you can leave out the subject of the verb in many cases. Yo me llamo Alejandro, my name is Alex, and me llamo Alejandro, my name is Alex. They mean the exact same thing, but in many languages, not just Spanish, although Spanish is the one I know best, you're allowed to leave out the subject of the verb. So whether or not people actually do what's allowed in that language or do more than what's allowed in that language is just a matter of convention. Likewise here, Z star Z is just convention, but on any test or assignment in this class, if we're dealing with numbers as opposed to matrices, Z star Z is fine. Anyway, Z star Z would be A minus BI times A plus BI. So when we do the FOIL, we get A squared plus ABI minus ABI minus B squared I squared, which is A squared, and these cancel. Minus I squared is minus -1, and minus -1 is the same as +1. So A squared plus A squared plus B squared. So people will often write that the magnitude squared or absolute value squared or modulus squared or length squared of Z is equal to Z star Z. Any questions? All right. Let me see if there's anything else I want to do here. Let's go to some questions that I have for you. So I'm going to share my other screen. Now, we can't do polling here. And because we can't do polling, I'm just going to show you this. If Z equals A plus BI, then what is Z star plus Z?
It is A minus BI plus
2A?
It's
B.
2A.
Yeah, it's going to be A plus BI plus A minus BI. So it's going to be 2A. Any questions? All right. Then how about this? What's the magnitude squared of Z star minus the magnitude squared of Z?
Would it be 0?
0.
Yeah, let's drop answers in the chat from now on rather than talking. Yeah, it's going to be, I just want to, well, actually, there's no good way to poll here. And I just realized an even more serious problem. I want to poll you. I want to do polls next time because that way everybody gets to weigh in before seeing the first person's answer. The problem is that I can't do writing on my laptop, but I can't do recording on my tablet. Zoom doesn't let you record on a tablet. So if I want to record this and share it to YouTube, I have to be logged in from my laptop. But if I want to do anything freehand, I have to be on my tablet. And if I'm on 2 devices at once, then Zoom disables polling. So I need to think about that. All right, let's talk about why this is what it is. The magnitude squared of Z, well, it's just A squared plus B squared. Now, the magnitude squared of Z star, we'd replace B with -B, but when we square -B, we just get B squared again. So Z star and Z have the same length, the same absolute value, the same everything. So the only thing they differ in is the sign of their imaginary part. So that difference would be 0. All right. Now we're not taking absolute values anymore. Now we're asking what's z star squared? Not absolute values squared, just z star squared plus z squared. And that one you're going to have to do some algebra with. You're going to have to actually write things out on a piece of paper in front of you. So we'll take a minute for everyone to write that out, try it, and then we'll talk about it. All right, a lot of people are answering. The answer is 7. And since there were some wrong answers about that, let's switch back to my other device and I will write that out. So z squared is a plus bi squared is a squared plus 2abi minus b squared, right? Because we're just squaring something. This is ib squared over here. Well, z star squared is going to be a minus bi squared. And so that's going to be a squared minus 2abi minus b squared. And so when I add up these two quantities, these reinforce each other, so we get 2a squared. These cancel. And then the minus b squareds are the same in both. And so we wind up getting that. And just a minute. Any questions on that? How did I get a minus bi for z star squared? All right, so z star is a minus bi because z is a plus bi. And so z star, we just take the negative of the complex conjugate. So z star squared is a minus bi times a minus bi, or a squared minus abi minus abi, and then plus I squared b squared. So that's a squared minus b squared minus 2abi. Does that answer your question? All right, so now let's talk about what we would do if we had a complex number in a denominator. So let's talk about 1 over a plus bi. 1 over a plus bi, we want to somehow get this into the sum of a real part and an imaginary part. And so what we want to do is we want to get all the imaginary numbers out of the denominator. We can write this as the same thing multiplied by the conjugate on top and bottom. And we know that if we multiply by the complex number by its conjugate, then we get this, a minus bi over a squared plus b squared. Any questions? This is only one of two major ways of manipulating complex numbers. In general, if you're given a formula and you have to do a whole bunch of addition and subtraction and cancellation of things, you're going to probably have to work with it this way. But I was drawing complex numbers in a plane. Of course, they have a length. Which I'm going to call r, because we're going to work in polar coordinates. This is our real axis. This is our imaginary axis. So r is a length or an absolute value. You'll see these terms used interchangeably. And then there is an angle. And we always have to be a little bit careful with those angles. In this case, it's pretty easy. Tan theta equals b over a. But what if our complex number were over here? So I'll call this b1 and a1, and I'll call this a2 and b2. This should be theta 1. Well, tan theta 2 is certainly b2 over a2. But if you were to run that through a calculator, if you were to just say, therefore, theta 2 equals arctan of b2 over a2, most calculators are going to give you an answer that's somewhere between 0 and 90 degrees, or 0 and pi over 2 radians. So be careful here. Add pi or 180 degrees when using a calculator. Well, we don't just do this so that we can draw things and calculate a few angles. It turns out that a very powerful tool is that z can be written as r e to the I theta. That any complex number can be written this way, as a length or absolute value. So sometimes people will write as z equals magnitude of z e to the I, and then they might call this the angle of z. Many textbooks, including ours, call it the argument of z, or the phase of z. These are all equivalent names. These are all names for the same thing. The angle, the phase, the argument, they all come from different conventions, but they all mean the same thing, that z equals something times e to the I theta. If we think about this geometrically, well, I'll work in this quadrant for convenience. This is r, this is a, but a must be r cosine theta, and this is b equals r sine theta. That's just as true in complex numbers as it is in trig. And so a plus bi must be equal to r cosine theta plus I r sine theta. And we know that this is r e to the I theta. So e to the I theta is cosine theta plus I sine theta. This is something that you hopefully saw in a previous math class. As a reminder, here's where it comes from. There's a Taylor series, and we're going to get into more depth on Taylor series in the following 3 lectures. But for now, we'll just take it as a given that you can write many functions in terms of a power series. And the power series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. So e to the I theta, by that definition, has got to be 1 plus I theta plus I squared theta squared over 2 factorial plus I cubed theta cubed over 3 factorial plus I to the 4th theta to the 4th over 4 factorial and so forth, or 1 plus I theta minus theta squared over 2 factorial minus I theta cubed over 3 factorial plus theta to the 4th over 4 factorial, because as we saw above, I to the 4th is 1, I cubed is minus I, and I squared is minus 1. And if we just start grouping terms, we are going to get 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial, etc. Plus I times theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, etc. And this is the Taylor series for cosine theta. This is the Taylor series for sine theta. Any questions?
Just a comment. That's cool.
What?
The comment.
A
That's
comment
cool.
that's cool?
Yes.
Oh, here's something even cooler. This is a fact that's sort of obligatory to recite. So e to the I pi is going to be cosine of pi plus I sine of pi. Now the cosine of pi is the cosine of 180 degrees, that's -1. The sine of pi is the sine of 180 degrees, that's 0. So e to the I pi plus 1 equals 0. And we have 5 of the most important numbers in all of math here: e, I, pi, 1, and 0. And they all show up in a single formula. And so it is obligatory to write this down as soon as you discuss e to the I theta. This was, according to Richard Feynman, one of the great physicists of the 20th century. He taught himself a lot of math in high school. When he learned this formula, he wrote down something to the effect of the most amazing formula ever. So we can conclude then that e to the I pi is -1. What about e to the I pi over 2?
Just I.
Yep, that's going to be cosine of 90 degrees, which is 0, plus I sine of pi over 2, or 90 degrees, which is 1. Now, this is actually a very useful way of writing complex numbers as soon as we want to do multiplication, division, and powers. Because for starters, if we raise z to the power n, we wind up getting r to the n, e to the I, n theta. And I would much rather take the cosine of n theta and the power of r to the n than have to multiply a plus bi by itself n times. And I really wouldn't want to do square roots the old-fashioned way here. But the square root of z is trivial. The square root of z is z to the 1/2. So that's the square root of r, e to the I theta over 2. And of course, if I wanted to take a cube root or a fourth root or some different power altogether, like the 1.7 power of something or the 0.321 power, well, again, z to the 0.321, something I picked just because it doesn't mean anything in particular. There's no trick for doing it by hand. Z to the 0.321 power would just be r to the 0.321 power, e to the I times 0.321 theta. Any questions?
Someone's asking in the chat, can you explain how you got to theta over 2?
Theta over 2, oh, because square root of z is z to the 1/2 power. All right, so when we take something to the 1/2 power, if I had e to the x to the 1/2 power, that would be e to the x over 2, or e to the 1/2 x. So whenever you take the square root of something, you're raising it to the 1/2 power, all exponents get multiplied by 1/2. So let's think about what the complex conjugate means in these terms. All right, here's z, here's theta. We know that z star, we just flipped the imaginary part. When we flipped the imaginary part, we took that angle and multiplied it by -1. So z star should be r e to the minus I theta. Make sense? And then 1 over z, well, that should be 1 over r e to the I theta. And some people ask, do we handle exponents the same way here? You know, if I had 1 over e to the x, that would be e to the minus x. And 1 over e to the I theta is indeed e to the minus I theta. So what we've got here is that 1 over z is 1 over r e to the I theta is 1 over r e to the minus I theta. So we notice two things. We notice that the length of the complex number got inverted. The absolute value of z is inverted, and that the angle got flipped. Now we could also, if we wanted to, do this as 1 over z times z star over z. And we would be left with z star over the length of z squared, or r e to the minus I theta over r squared, which is exactly what we would have gotten if we had taken 1 over a plus bi times a minus bi over a minus bi. We would have gotten a minus bi over a squared plus b squared, which is the same thing as r squared, and this is r e to the minus I theta. Questions? Well, we can do more than just play with one complex number. We can multiply complex numbers this way. So Z1, Z2 would be R1, R2, e to the I theta 1, e to the I theta 2 equals R1, R2, e to the I theta 1 plus theta 2. Z1 over Z2 would be R1 e to the I theta 1 over R2 e to the I theta 2, or R1 over R2 e to the I times theta 1 minus theta 2. Any questions? So what's IZ? IZ, let's do this two different ways. Let's do I multiplied by Z, both in terms of A plus BI, what some people call the Cartesian form because Cartesian coordinates, and in the R theta, or the polar form because of polar coordinates. IZ would be I times A plus BI is IA minus B. It would also be IR e to the I theta, or R e to the I theta e to the I pi over 2, or R e to the I times theta plus pi over 2. Looks to me like this is a rotation. All right, all we've done is we've taken this complex number and we have rotated it. So if this was A plus BI, let me make that a little more, oops. Trying to erase. Why is my eraser not working? Okay, there's my eraser. All right, so let's make this a really exaggerated complex number just to illustrate the point. So this is A is really large, B is really small. Then we flip it around, so suddenly the imaginary part is large and the real part is small. So this is IZ and this is Z. Doesn't that kind of look like it's been rotated 90 degrees?
Yeah.
Yeah, the Cartesian form sure looks like it's been rotated 90 degrees, and the polar form is definitely rotated 90 degrees. Conversely, if I made these equal to each other, so now here's A and here's B, well, A and B will still be equal in magnitude. It's just that one of them got flipped, went from positive to negative. So again, looks like a 90-degree rotation when I draw something in green. So no matter how I do this, multiplying by I is the same as rotating by 90 degrees. And more generally, Z e to the I phi equals R e to the I theta e to the I phi equals R e to the I theta plus phi. So what we've got here is a rotation through an angle phi. So complex exponentials are just rotation operators. They're just things that take a vector in the complex plane and then rotate them. So now I am going to, again, share my other screen. And great, I need to, great, how did I turn off the presenter form last time? No, That's not what I wanted. No. Okay, well, great.
Display settings on top, maybe.
Well, I've already shown you the answer. So if z is r e to the I theta, z over z star, well, for z over z star had better have absolute value 1, because whatever that r might be, r is the absolute value of this z, but whatever that r is going to be the same in z and z star, so that's going to cancel. So it can't be 6 or 7. So then it's just a question of, is it 1? Well, z has e to the I theta, z star has e to the minus I theta, so it can't be 1. The top and bottom are different. So we're going to have e to the I theta divided by e to the minus I theta, or e to the I theta minus negative I theta. So it has to be this. Any questions?
Has anybody in this party ever committed a felony?
I can't quite hear you. What'd you say? Whoever just asked that question, could you repeat? Yeah, I'm just going to switch to my other device and sketch out the answer. And I've got to share that screen. All right, z over z star will be r e to the I theta over r e to the minus I theta equals r e to the, sorry, the r's cancel, e to the I theta, e to the minus I theta. Minus minus is a plus, so we get e to the 2I theta. Any questions? FBI came to take away his pirated textbooks. Okay, well, I don't know who that happened to, so I don't want to joke about the possibility that someone really is in some sort of trouble. But I will say about pirated textbooks, I once had someone ask me, those of you who have taken a class with me before have heard this story. Someone once emailed me to say, Professor, I found this PDF of the textbook. Can I use it? Is this the same as the book we're going to be using? And first of all, I can't really, I'm a state employee. I cannot use my work email to tell you to go ahead and violate copyright law. Even better, the PDF was on a server in a country that, let's just say, is not exactly on the US government's good guy list, all right? Whether or not you personally think this government is good or bad, or whatever you think of your foreign policy, I don't care. If you send me a link to a file that's been pirated and put on a server in a country that's on very, very bad terms with the State Department, do you really want me using my work email to say, yes, go ahead and violate copyright law with help from a public institution in a country that's on the State Department's bad list? Do you really think I can do that? But, you know, they thought I could do that. All right. I want to go over the assignment that was due today to get everyone on the same page there. So I'm going to again share my other screen. Let's just go over the solutions to this. All right, most people got the first part. They all got that z star is 3 minus 4i. A common mistake I noticed on the second part was either that people would leave the I in here when squaring the -4, so they wind up getting 9 minus 16 instead of 9 plus 16. That's very bad. Or sometimes they would get 16 minus 9 when they were dealing with IZ. Then the other thing that would happen is that people would get confused between the absolute value and the square of the absolute value. So a lot of people said 25 instead of 5. That's more forgivable. Most people got this part correct in that they knew how to take 1 over z, but then they didn't tell me which part is which part is the real part. And it's the 3 over 25. And you might think, well, aren't I just nitpicking there? Well, I'd love to say, oh, if you wrote this, then I assume that you know that the real part is 3 over 25. The problem is that over here, a lot of people point to the -1 multiplying the I and said, look, -1 is a real number. Well, yes, it is a real number, but it's not the real part of 1 over I or the -I. Almost everyone got 7 and 8. The mistakes were usually just some sort of little arithmetic error at the end. And on question 9, almost everybody got 5 square root of 2. Any mistakes that I saw here were usually mistakes that I also saw in 2 and 3. Any questions from you guys before we move on to the next topic? Question about number 9, and then, so Nicholas, what's your question about number 9?
I just want to see if my answer was correct. You didn't scroll down.
You want to see if your answer to number 9 is correct? Oh, yeah. Because z plus iz is 3 plus 4i plus 3 times I plus 4 times I times I is 3 plus 7i minus 4 is -1 plus 7i. So that's the square root of 1 squared plus 7 squared, or square root of 50, or 5 square root of 2.
Thank you.
All right, and then Stephen, you have a question about the attempts. Okay, if you do more than one attempt. If you do more than one attempt, what happens is that it shows me them one at a time, so I just grade what I see in front of me. But if you submitted 2 different things, it's your grade on the second one that you submitted that will actually go into the grade book. So you'll see what you got on both of them, but only the second one will go into the grade book.
So if you submit it ahead of time and you grade it and you point out mistakes and we correct those, we can resubmit it with the corrections for more points?
Yes, that is what the policies would allow. I'm uncomfortable committing to lots of grading in advance. I did some grading in advance last night just because I had a feeling that I wouldn't have myself right in front of the laptop first thing at 9 o'clock this morning. So I can't promise that if you I can't promise that I will always be doing lots of grading in advance, but yes, I suppose that is the way it works. You start asking questions about fairness and whether that is a reasonable policy for grading. I'm uncomfortable committing there. It's just kind of one of those things of working around it like this. If you really want to push on questions about whether the grading policy is technically fair, all I can say is apply to med school. Because I don't know about you guys, but when I was a freshman, all of the pre-meds in my chemistry class were essentially pre-law when it came to grading. All right, let's move on. Let's talk about why we use these. We've been dealing with the arithmetic and algebra of complex numbers. Now let's use them. We use them because oftentimes in physics, you have some oscillating quantity. F of t is an amplitude times cosine of omega t plus a phase. And that is often written as the real part of a e to the I omega t plus phi. because this quantity here would actually be a cosine of omega t plus phi plus ai sine of omega t plus phi. But this is the only part that remains after you take the real part. And so we deal with oscillating quantities this way in physics. Now, you could ask, why do we deal with oscillating quantities that way? Why go through this extra step of abstraction, bringing in these numbers that are quite literally imagined rather than sort of natural parts of the real world? Well, because let's say that we've got the sum of two oscillations. We've got A1 cosine of omega t plus phi1 plus A2 cosine of omega t plus phi2. And we want to figure out, we know that these oscillations are going to add up and they're going to produce an oscillation with a new amplitude that may be larger than either of the two original amplitudes, maybe smaller than either of them. You know, it could be, for instance, that they cancel out. That one of the oscillations looks like this and the other one looks like that. It could be that they reinforce because one of them looks like this and the other one also looks like this. And so together they just look like that, or anything in between. And we could deal with these cosines, but if we dealt with these cosines, then we would have to use a whole bunch of trig identities. We would have to use the fact that cosine of omega t plus phi is cosine omega t cosine phi minus sine omega t sine of phi. I don't want to have to add all those up and then do even more trig identities as we go along. What I want to say is that whatever this might be, that this is somehow equal to r, this is equal to the real part, excuse me, of r e to the I omega t plus phi. Now there are two ways that, or I'll call it theta here just to be clear, theta. There's two ways that we could get r and theta, and both of them are easier than dealing with a whole bunch of trig identities. One is to say that that I could rewrite the left side as the real part of e to the I omega t times a1 e to the I phi1 plus a2 e to the I phi2. And that's equal to the real part of r e to the I theta e to the I, omega t. So then a1 e to the I phi1 plus a2 e to the I phi2 is r e to the I theta. Now, if I take the real part of each side, I get a cosine of phi1, a1 cosine of phi1 plus a2 cosine of phi2 equals r cosine theta. And a2 sine, start over. a1 sine of phi1 plus a2 sine of phi2 equals r sine theta. So I take the ratio of these two quantities, and if I take bottom over top, if I flip these, I'm going to get the tan theta, my bad. Tan theta is a1 sine of phi1 plus a2 sine of phi2 over a1 cosine phi1 plus a2 cosine phi2. That is a way to do it. I get tan theta. And once I've got tan theta, I can take the arc cosine, take theta, and say that r is equal to a1 cosine phi1 plus a2 cosine phi2 over cosine theta. That is an algebraically valid way of doing it. First step, I take a ratio here, I cancel out the r's, I solve for theta. Second step, I use the fact that in this equation, everything on the left side is known. A1 and phi1 and A2 and phi2 are known. And on the right side, theta is now known, and r is the only unknown, and I solve. That is a valid way. Is there any question on that before I show you another way?
Just a quick question on your handwriting. So right up the top, right below the horizontal line, you have the real part of e I to the omega t. If you move over two more terms, is that a2 e to the theta phi 2?
I phi 2. So
I phi 2, okay.
yeah. Any other questions? Well, what I wrote out here is algebraically valid. It's not particularly insightful. So let's look at another way of doing this, which is to use the fact that the absolute value of r e to the I theta is equal to the absolute value of a1 e to the I phi1 plus a2 e to the I phi2. And if the absolute values are the same, the squared absolute values are the same. So on the left side, the squared absolute value is just r squared. And on the right, I can take this whole thing and multiply it by its complex conjugate. And when I multiply by the complex conjugate, again, we just do FOIL. We're going to get a1 squared because the e to the I phi cancels out e to the minus I phi. And I'm going to also do this one, doing the two easy ones first. Then if I multiply this by that, I get a1, a2, e to the, I times phi1 minus phi2. And if I multiply this by this, I get phi2 minus phi1, which is the same as minus phi1 minus phi2. And this, when I add up e to the I something plus e to the minus I something else, if I take e to the I x plus e to the minus I x, I get cosine x plus I sine x plus cosine of minus x, which is just cosine of x, plus I sine of minus x, which is just minus I sine x, because cosine is an even function and sine is an odd function. So these cancel, and I'm left with 2 cosine of x. What that means for all of this is that e to the I phi1 minus phi2 plus e to the minus I phi1 minus phi2, well, that's 2 cosine. So I'm left with r squared equals a1 squared plus a2 squared plus 2a1 a2 cosine of phi1 minus phi2. And this is a much more insightful way of getting the amplitude. You know, when I add these oscillations, this is a much more insightful way of getting the amplitude of the combined oscillations in terms of the individual amplitudes and the phases versus doing it this other way, which is certainly valid algebra. If you were given a bunch of numbers and you faithfully plugged and chugged and turned the crank on the calculator, you would get the right number out of that in the end. But it doesn't provide the same insight, which is that this third term here, this third term will add constructively, the cosine will be positive for certain values of the phase difference, and it'll add destructively, the cosine will be negative for certain other values of the phase difference. So it relates constructive and destructive interference to this phase difference. All of you were, whether you took it here or you took it elsewhere and transferred here, at some point you took some class where you had some optics and you learned about constructive and destructive interference of light waves and sound waves, and they all had to do with that phase difference. This formula is telling you that the amplitude of a combined wave depends on the amplitudes of the two waves you added and the cosine of the phase difference. Any questions?
I just have a clarifying question, but it's not for this.
Yeah.
So the thing we did this past Friday, you already mentioned this, but just to make sure, it's not something we're turning in, right?
Correct. Fridays are graded entirely on participation. If I see you in the group contributing, boom, participation points. There were no points for this past Friday because it's the first day some people haven't added yet, but starting this coming Friday, there will be points for that. The only time you have to show me anything from Friday is if you weren't present during the Friday discussion. All right,
Okay.
forward. On Wednesday, we're going to do a few more examples with complex oscillations. Then we'll start on power series. I will try, I think this two device Zoom meeting is not going to work very well. So I think realistically, I'm just going to have to get some sort of writing tablet that I can hook up to my laptop. I'm gonna have to see if the university will buy it. If the university cheaps out on me, I'm gonna have to see what's on sale. So for a little while, we're not gonna be doing polling, but once I'm able to do everything on just one device, then we'll start doing polling. For now, the questions I wanna show during class will just be discussion questions. But with that, the formal session is done. I'll stay logged in for a few minutes if anyone has questions. And I will